did a verification for the first 3 cases. Yeah. Here, although we do not have to, in order to apply, in order to apply mathematical induction, so here our goal, we want to apply mathematical induction. Mathematical induction. In order to apply mathematical induction, we only need 2 cases. 2 base cases. We already did 3. Why 2? The reason is simple. Look at the right-hand side terms. There are 2 terms. So we only need 2 cases. If you have 3 terms, then we need 3 cases. And so on. Okay? Yeah. So we only need 2 base cases. Yeah. We did 3 already enough. Yeah. So here, I like to do another one, case number 4. The reason is I want to practice. I want to show you some special way in calculation. Yeah. So practice, for practice purpose. Yeah. All right. So let's look at case number 4. When n equals 3, we want to verify f3 equals this expression if it equals f3. Yeah. f3, we calculate f3 equals 2, right? Yeah, because 1 plus 1. Yeah. f1 plus f2, they are both 1. They are both 1, so f3 should be 2. So we want to see if this f3 equals 2 or not. Yeah. But here, we don't want to do the straightforward calculation as the previous case. Yeah. Too much computation. Here, I want to use the special properties of golden ratio. Here we use the golden ratio. Why not? We just apply some special properties of the golden ratio to make our computation easier. Yeah. All right. Yes. Here I show you the method. Yeah. When we look at the expressions inside the parentheses, golden ratio phi cubed, that 3, the degree number 3, relatively hard. Yeah, because if we want to expand that golden ratio number 1 plus root 5 over 2 raised to cube, a lot of computation. Yeah. So due to that, the fact, the degree too high. Yeah. So here, our understanding is like this. If we can bring down the degree, if we can lower down the degree of the golden ratio, then we can make our computation easier. Yeah. The higher the degree of the golden ratio, the harder the computation. Yeah. So our goal, we want to apply the special properties of the golden ratio to bring down the degree of each term. Yeah. First term, second term. Yeah. All right, so here, let me show you the method. Yeah. How to reduce the degree phi cubed. Yeah. All right. So first, we need to know the basic properties of the golden ratio. So there are 2 basic properties for the golden ratio. Yeah. Yeah. All right. The first one, 1 equals phi squared minus phi. The second one, phi squared equals phi plus 1. These 2 basic properties for the golden ratio. Yeah. Yeah. So if you ask me why, how do you get these 2 properties? That's very simple. Yeah. How do we derive calculated the golden ratio. Yeah. Because golden ratio phi is the root of this quadratic equation. X squared minus x minus 1 equals 0. That means if you plug in the golden ratio phi into this equation, we should have the equality phi squared minus phi minus 1 equals 0. Yeah. You can, if you plug in, you get 0, right? Yeah. Phi squared minus phi minus 1. Because we calculate from that equation. Yeah. All right. So from this equation, can you move terms around? You can get the first one, 1 equals phi squared minus phi. Yeah. You move, minus 1, that term to the right-hand side, so you get 1 equals phi squared minus phi. Yeah. Or you move these two terms to the right-hand side, you get phi squared equals phi plus 1. Okay? Yeah. Yeah. So these two properties, when we need to bring down the degree of the golden ratio expression, we need to use these two properties. Yeah. So let me show you. First one, phi cube. Bring down phi cube expression, the degree. Now, so we find another expression using the golden ratio, but with lower degree, lower than degree 3. Yeah. All right. To do that, let's split. Phi cube equals phi times phi squared. Yeah. Then phi squared, when you see phi squared, you can apply the second property. Replace phi squared by phi plus 1. Okay? So equals phi plus phi times phi plus 1. Yeah. All right. So then equals phi squared plus phi. So you see phi squared another time, right? You see phi squared another time. Then replace phi squared by phi plus 1 another time. You get 2 phi plus 1. 2 phi plus 1, this expression, degree lower, degree 1 is much lower than degree 3, so it should be much easier to calculate degree 1 expression. Yeah. All right, so that's the phi cube. There, 1 over phi cube. This time, I want to bring down degree at the denominator. Denominator, bring down. Okay, all right. Yeah. So let me use a different way to bring down. Because degree bring down, we know, when we have a common factor between numerator and a denominator, we can do cancellation. Yeah. Here, we want to do cancellation. Numerator, denominator. But numerator is 1, no factor, right? No factor other than 1. Okay? Yeah. But remember our property 1. Can we replace 1 by phi squared minus phi? Yeah. If we replace 1 by phi squared minus phi, you have common factor phi. Okay? Yeah. Let's do the replace. Phi squared minus phi over phi cubed. The first property of golden ratio. Now we can do cancellation. Okay? 1 common factor phi cancellation. Yeah. Now it becomes phi minus 1 over phi squared. Yeah. All right. Yeah. So the denominator degree is lower. 2. Yeah, degree 2. Yeah, lower than degree 3. Yeah. Now let's do further cancellation. Further cancellation. So you see 1, another 1 in the numerator. Can we replace this 1 by another representation, phi squared minus phi? Yeah. Another property number 1, substitution another time. Okay? Yeah. So we get a 2 phi minus phi squared over phi squared. Okay, yeah. Let's do simplification. 2 over phi minus 1. 2 over phi minus 1. The degree of the denominator lower, yeah. This time phi, yeah, phi, yeah. All right, yeah. Now we are ready. We can calculate phi cube plus 1 phi cube, yeah, with our new representations. Okay, new representation: -1, +1 cancel out. 2 factor out, phi plus 1 over phi. Phi plus 1 over phi. Okay? Yeah, this new representation. That new representation, if we multiply 1 over root 5, both sides, 1 over root 5, so we get a F3 equals 2 times F1. Yeah? Yeah? Yeah. When you multiply 1 over root 5, yeah. Right? Yeah, because that expression, like F3 expression equals F1 expression, right? Yeah. And we know F1 equals 1, 2 times 1, and that's 2. That tells us F3 equals 2. So that's the verification for F3. Yeah. But this time, you can see we apply the 2 basic properties of the golden ratio. Just to give you a simple example, how to apply the 2 properties of the golden ratio to simplify any expression with golden ratio. Any expression with the golden ratio. Okay? Yeah. Before the midterm, I will not give you such questions. Yeah. So, simplify expressions with golden ratio. So I will delay after the midterm. Okay? After the midterm, in our homework assignment number 2, yeah, I will give you a few questions. So you need to simplify golden ratio expressions using these 2 properties. Yeah. All right. Yeah. So I saw a chat message. Let me check it. Yeah. All right. Yeah. So here. Yeah. Okay. Any new message? All right. Okay. All right. Yeah. No new message. Yeah. All right. So let's continue. Now, let's move to mathematical induction. Yeah. D.2. Verify Fibonacci formula, the general case, by mathematical induction. Yeah. All right. Yeah. So the powerful tool, mathematical induction. Yeah. All right. So let's review 3 basic steps of the mathematical induction. Yeah. Step 1. Verify the base cases. We did it. Yeah. So check the base cases. Yeah. Yeah. So we only needed to verify 2 base cases because there are 2 terms here. Yeah. So 2 base cases enough. Yeah. If you have 3 terms, you need to verify 3 base cases. 4 terms, you need to verify 4 base cases, and so on. Okay? Yeah. Yeah. 2 cases. All right. F0, F1. Yeah. Step 2, mathematical assumption. Yeah. You just make assumption, induction assumption. Yeah. Induction assumption. Yeah. All right. So what the induction assumption we want to make here is assume that the formula is true for 2 less than or equal to k or less than or equal to n. Actually, this lower range, we can expand to 0. Because, so here, here it's better to write, although we write an assumption here, because assumption, so you cannot assume, so here, we should handle this assumption carefully. Okay? Yeah. So yeah, let me to get a better 0 less than or equal to k less than or equal to m. Yeah. With n greater or equal to 1. Yeah. Yeah. So a better way to write this assumption. Yeah. So here, because here we assume too much. Yeah. Although, so here we assume too much. Yeah. Because if we only verify the first base cases, we should not assume more than we have, right? So here, this one we assume. Yeah. So here, I point out the problem. Okay. We assume too much. More than we have. Okay? What do we have? We can assume this much. Okay? We can assume this much because we verify 0 and 1. Okay? Yeah. Now, when k between 0 and n with n greater or equal to 1. Okay? 1 is the smallest possible value for n. N could be larger. Okay? N could be larger. But in order to make n larger, we need to do some work to make n larger. Step 3. Step 3. In step 3, we will show we can enlarge that n. By step 3, enlarge that n. Okay? Then this assumption is correct. Otherwise, you assume something you don't have. That's not right. Okay? That's not right. Yeah. All right. Yeah. So here, yeah. Let me update that assumption, that condition. Yeah. All right. Assumption condition. Okay. All right. There. Yeah. So here, so what's the assumption after the condition? The assumption is the this Fibonacci number formula is correct. Yeah. When k is in this range, when k is in this range, this formula is correct. That's the assumption. If k is out of this range, then we cannot use this formula. Only when k falls into this range, we can use this formula. That's the assumption, the induction assumption. All right. All right. Step 3, verify. Now we want to expand the upper bound of the range, n. And n is the upper bound of the range. We want to make it larger as possible. Yeah. So by step 3, we want to show it's legal to expand the upper bound of the range by 1, only by 1. Every time we increase that range only by 1 number. Step 3, we will show that. Okay? Yeah. So that means step 3, this formula is true for n plus 1. Yeah. N plus 1, we have the same formula. That means we expand the range by 1. Okay? Expand the range by 1. Yeah. We can expand. Yeah. If you expand by 1, it's legal. Okay? Yeah. By 1, it's legal. By 10, may not be legal, but by 1 is legal. Okay? Yeah. All right. So that's the 3 steps of mathematical induction. Yeah. Here you can see we only need to do step 3. Yeah. Step 1 we already have. Step 2, induction assumption. Yeah. Just write a statement. That's all we need. Okay? Write a statement. Yeah. Induction 3, we need to do the mathematical work. Step 3. Okay? Yeah. Now let's do the work. Okay? Formula transformation. Yeah. All right. This recurrence relation is given. Yeah. It must be true. Yeah. It's given. Yeah. So we can use this formula. Okay, all right. Then, now, the first Fn, can we write Fn in this expression? Yeah, the first question. Second question, can we write F sub n minus 1 in this second expression? Yeah. First, we need to make sure it's correct. We can use these two expressions. Yeah. All right. Yeah. The answer is yes. The answer is yes. Yeah. Why? Let me explain. Why we can use these two expressions. Yeah. Yeah. All right. Let me do later. Yeah. Let me show you why it's legal to use these two expressions. Let's recall the range in our induction assumption. The range. What's the range? The range in our induction between between 0 and n, all right? Yeah. And yeah. Although with n greater or equal to 1. Okay, all right. So now we need to check, is n in the range? Yes, last one. Upper bound. N is in the range. Upper bound. Yeah. All right. N minus 1 in the range. Yes. Yeah. 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 So both subscripts n and n minus 1 are in the range. So it's legal. We can use these two expressions. It's legal. Okay? All right. Now, let's do the, transformation. Yeah. So we factor the common factor 1 over root 5 out, and inside the big parenthesis, let's move the power of phi terms together and two fractional forms together. Yeah. Yeah. Or we here we group. Yeah, so here you can see we group four different terms. We do the grouping, group them based on the structure. We group these 4 terms based on the structure. The first 2 terms, they have the power function structure. Okay? Power of golden ratio structure, the first 2 terms. The last 2 terms, they have similar structures. Yeah. So we group them based on the similar structures. Yeah. All right. So after that, then we want to compare. We want to compare the goal. Okay? Yeah. So the goal, verify that one. So that's the goal. Okay. So you compare the goal expression and the current expression. 1 over root 5, they both have 1 over root 5. We can ignore, right? Yeah. So we only want to make sure the expressions inside the big parenthesis the same. Yeah. We only want to, prove the part inside big parenthesis the same. Yeah. But when you look at the part inside parenthesis, can we, so here we need to use our imagination in order to show they are 2 same expressions. We can reasonably guess. Here we do some guess. Reasonably guess. Yeah. The power function part should be the same. Yeah. The term with same structure should be the same. And the fractional part should also be the same. Yeah. So, so the same structure. Yeah. So here, that's our guess. Okay. So these 2, this is our guess. We haven't proved them. We need to prove these 2 equalities. No. But before we prove, we want to make a guess first. Guessing, in problem solving, guessing is very important. Guessing, if you can make good guess, correct guess, close guess, good guess, then you can find a path toward your solution faster. When you make a guess, actually, you are moving toward your destination with a good guess. Here, we are doing that. So let's show the first equality. We need to prove the first equality. Okay, all right. When we prove, we start with this golden ratio property. Phi squared equals phi plus 1. That's our second golden ratio property. Yeah. So when we start from this equality, can we multiply the same non-zero number both sides of the equality? This time we multiply phi to the negative minus 1. It's a non-zero term, right? Non-zero term. We multiply both sides of the equality. It's also correct. Yeah. All right. After simplification, so you get phi to the n plus 1 equals phi to the n plus phi to the n minus 1. That's exactly the same equality we guess at the beginning. Next, so we have more confidence. Our second part of our guess should be correct. Yeah. So now we want to prove it. So we have more confidence to prove the second expression equality is correct. Yeah. All right. So let's do the proof. Yeah. So this time, our goal, we want to show this inequality is correct. Yeah. Yeah. It is harder than the first one. Yeah. But this time, we use another commonly used problem-solving method. It's called backward thinking. Backward thinking. Yeah. So we assume if this equality is correct, what can we get? Yeah. Yeah. Because this is our destination. This expression, this is our destination. Okay? The end, right? That's the end of our proof. Yeah. So we start from the destination, going backward. Okay? Yeah. Going backward. So starting from the end, then moving, backward direction. Yeah. So we call it backward thinking. So here we use the backward thinking here. Yeah. So if the destination equality is correct, then we remove the common denominator by multiplying phi to the n plus 1 both sides, so we get this equality. Yeah. This equality should be true. Okay? All right. Yeah. And the relationship between these two formulas, we can go both ways, right? Yeah. If the second one is correct, we can get the first one. If the first one is correct, we can get the second one. So both directions, yeah, correct. Yeah, we can do deductions, both directions. All right. Then, let's assume if this is correct, how can we simplify it? Yeah. Because the power of -1 looks quite annoying. We want to simplify the power of -1. Very annoying. Yeah. Yeah. So now, let's multiply appropriate power of -1 to make it simpler. Yeah. Yeah. So what power of -1 we should multiply? Here, -1 to the n minus 1. This power of 1. -1 to the n minus 1. If you multiply this expression to the left-hand side, it's 1. Yeah? Because n plus 1 plus n minus 1, you get a 2n. -1 to the 2n, it's 1. -1 to the even 2n equals 1. Okay? All right. So you get a left-hand side 1, right-hand side, coefficient of phi square is positive 1, is 1. Coefficient of the phi, negative 1. So you get simplified form without the power of negative 1, like this expression. And this expression is exactly the first property of phi. Yeah. Is it the first property of phi? Okay? The first property of phi, it's correct. Yeah? So if it's correct, then because the deduction, we can go both ways, right? Yeah. Yeah. If the last one is correct, yeah. So now our backward thinking, because both ways deduction correct. Okay. So the last equality is correct. Now, by this direction, deduction, this must be correct. Okay. If this is correct, yeah, we can go that direction. Then our destination formula must be correct. Destination equality must be correct. Or, both way, two-way deductions. Okay? Two-way deductions. Yeah. Yeah. So then our conclusion, the formula for f sub n plus 1, this formula, is correct. That means we can expand the range from n to n plus 1. Okay? By step 3, we can expand the range. Original range, k between 0 and n. But after step 3, after the work we just did here, we can expand the range from n to n plus 1. Okay? If we can expand range from n to n plus 1, can we expand the range from n plus 1 to n plus 2? One more, right? Every time we expand the range, one more. Yeah. And we can do the expansion forever, right? Yeah. It's legal to do the expansion like this forever. Okay? Can we cover all the integers? By expansion like this, we can cover all the integers, all the positive integers. That means we have shown the Fibonacci formula is correct for all positive integer n. Yeah, because we covered. Yeah, mathematical induction. The step 3, we can expand the range. Yeah, even if you give me that little n is 1 billion, 1 billion, that big, our expansion, sooner or later, we will cover that, right? Every time we just plus 1, sooner or later, our expansion of the range will cover 1 billion, right? So any number will be covered, okay? That's the power of mathematical induction. That's the power of it. You just prove one case, okay? One from n to n plus 1 case, then it works for all the cases, all integer cases. Yeah. That's the power of mathematical induction. Okay? Yeah. All right. So that's the mathematical induction. Only time I want to show you the power of mathematical induction. Yeah. All right. Yeah. So we finished this topic. Yeah. All right. All right. Yeah. Okay. Yeah. There. Our last topic, D.3, linear recurrence relations. Yeah. So solve. Yeah. Actually, we want to solve linear recurrence relations. Yeah. But we solve two types. Yeah. first order and the second order, these two. Yeah, higher order, too much work. Yeah, so we only do two lower order cases. Yeah. All right. The first one, now I want to go back to talk about our Tower of Hanoi problem. Remember, at this point, we have not known how many disk moves for n disk problem, right? Yeah. Remember, at the time when we solved that problem before, yeah, I gave you the answer when we have 3 disks. Yeah. So n equals 3 when we have 3 disks. The answer is the number of disk move, yeah, C of 3 equals 7. Yeah. Yeah. But when there are n disks we don't know, the number of moves solving that n disk problem, how many disk moves? We don't have that. Yeah. Here, let me find the solution. Yeah. Yeah. All right. Yeah. So here I want to show how to solve the simple recurrence relation. Yeah. All right. Yeah. First, oh, sorry. Yeah, so here, let me use the space here. Yeah, I need to write the solution here. Okay. All right. Yeah. Here you can see in this recurrence relation, the right-hand side, there is only one unknown terms. Not like Fibonacci recurrence relation, there are 2 unknown terms. Here we only have 1 unknown term. Yeah. That should be simpler. That makes this property, makes this equation simpler to solve. Yeah. So this one we called the first order recurrence relation. Recurrence. The Fibonacci one, second order. Yeah. 2 unknown terms. Okay, all right. Then, but this one has a +1 non-zero constant term. The Fibonacci one, Fn equals F sub n minus 1 plus F sub n minus 2. That this one has no non-zero constant term. Okay? Yeah. Yeah. So that's another property. Yeah. Yeah. And this non-zero constant actually make the question harder, make the question a little harder. Okay? Without constant term, that would be easier to solve. With constant, a little harder. Okay? All right. So our first step, we want to remove the constant. Yeah. So our first step, we want to remove the non-zero constant term. Right? To make it simpler, a little simpler. Yeah. The question is how to remove that non-zero constant. Yeah. Yeah. Here, we use a special technique. Yeah. All right. So let me write this equation again. C of m equals 2 times C of m minus 1 plus 1. All right. Yeah. Let's do the manipulation on this equality. Yeah. When we do the manipulation, in our mind, we should have some, reasonable understanding. Otherwise, you may do the wrong manipulation, right? So you need to, so you do some work, but your work would make you far away from the destination. Yeah. So we want to move closer to the destination, not far away from the destination. Yeah. So how to do that? So our goal, because our goal, we want to make that non-zero constant term, this term, disappear. We want to make that term disappear. Okay? Yeah. All right. So here, how to make it disappear? Yeah. All right. When you look at the structure of both sides of the equality, they are slightly different. Yeah. On the left-hand side, there is no plus 1 term. On the right-hand side, there is plus 1 term. It's the difference, right? The left-hand side, right-hand side, the structure different. Yeah. So our first step when we do the manipulation, we want to make the left-hand side, right-hand side the same structure. Yeah. So when they have different structure, we want to make them with the same structure. How to make them same structure? Left-hand side, no plus term. Right-hand side, plus 1 term. How do you make both sides same structure? Left-hand side miss something, right? Left side miss something. Can you add the missing part back to the left-hand side? To make it have that plus 1 term, right? Left-hand side miss that plus 1 term. It's missing. We can add it back. Okay? So let's add plus 1 to the left-hand side. But when you add a plus 1 to the left side, you must also add a plus 1 to the right-hand side to balance the equality, right? Otherwise, it would become inequality, right? So you have to add the same number both sides to make it another equality. Okay? All right. After you do this manipulation, and we do simplification, the left-hand side becomes C of n plus 1. Right-hand side equals 2 times C of n minus 1 plus 2. Okay? This time, both sides, they have that non-zero constant term. The structure-wise, same. Okay? Structure-wise, similar, right? Similar, then we can do the generalization, right? Similar structure, then we can do the generalization. Okay? All right. Yeah. How about this expression? We can use another function to represent. Because we want to make that plus 1 disappear, right? Remember? We want to make that plus 1 disappear. How do you make it disappear? Can we define a new function d of n equals c of n plus 1? That would make it disappear, right? In d function, you will not see plus 1. Okay? All right. Similarly, this one, you factor common factor 2 out. C of n minus 1 plus 1. Based on our definition, C of n minus 1 plus 1, can we use the d function to represent? Is it a d of n minus 1 by the definition? Okay? If we use the d function, now you have a 2 times d of n minus 1. Then the plus 1 term is gone, right? If you use the d form equality, d form equation, the plus 1 term is gone. Okay? Disappear. The plus 1 is gone. This new d function simpler than the old d function, right? OC function. Old equation. Old equation, you have plus 1. New equation, you do not have plus 1. Okay? New equation much simpler. Yeah. All right. Let's solve this new equation. Yeah. Can we do recursion another time? 2 squared times d of n minus 2. Right? Can we do another time 2 cubed times d of n minus 3? Okay. Can we keep going like this? Can we do iteration like this again and again? And at some point we get the general case 2 to the k times d of n minus k. Right? Yeah? Right? Yeah. Yeah. All right. Yeah. All right. Yeah. Then, let's look at the last step. 2 to the n minus 1. Okay, k equals n minus 1 times d of 1. D of 1. Yeah. We just make k equals n minus 1. Okay? Then n minus k is 1. And what is d1? What is this d1? d1, by the definition, because d of n equals c of n plus 1. So d of 1 equals c of 1 plus 1. What is c of 1? c of 1 equals 1. c of 1 plus 1 is 2. Okay? So that means d of 1 equals 2. So 2 times 2 to the n minus 1, that's 2 to the n. That's 2 to the n. Okay? 2 times 2 to the n minus 1, that's n. So that tells us, that gives us d of n equals power of 2, 2 to the n. And what is c of n? C of n equals d of n minus 1 by definition, right? So equals 2 to the n minus 1. Okay. C of n equals 2 to the n minus 1. Okay? So the formula is this 2 to the n minus 1. That's the solution. Yeah. And you can see if you plug in 3, 2 to the third minus 1, 7. Okay? 2 to the third minus 1, 7. Okay? Yeah. That's our old solution. Yeah. But the general solution, 2 to the n minus 1. Yeah. So the Tower of Hanoi, for n disk problem, in order to solve it, you need to make this many moves. 2 to the n minus 1. This many moves. Okay? Yeah. All right. So from this example, try to understand how to solve a basic linear recurrence relation. Yeah. In this one, first we try to eliminate that non-zero constant term to make it simpler. Yeah. Yeah. After we eliminate it, then we have much simpler recurrence relation. So we can find the solution in a much easier way. Yeah. Yeah. All right. But this is the first order recurrence relation. This example, first order recurrence relation. Okay. All right. Second order, next. Yeah, let me see, how much time do I have? Oh, only 8 minutes. Yeah, 8 minutes. Yeah, let me just talk about the beginning part. Yeah, yeah, because it's a long story. Yeah, this whole solution is a long story. So let me give you the introduction part of the second long story. Yeah. All right. First, the name of the equation. It's a very long, complicated name. Let me explain this long name first. Okay? Yeah. So let me read so what is that? The name of that equation. Yeah. Let me read the long name. Second order, second order, right? These two terms. Okay? Second order linear homogeneous recurrence relation with constant coefficients. That's the whole name of this equation. So let me explain the meaning. Second order, you already know it. Yeah. Okay. Linear homogeneous. Linear. Yeah. So the linear means each term is a linear function. Is a linear. Yeah. So you won't have the non-linear term. For example, fn minus 1 squared is a non-linear term. Okay? Yeah? Or the root of fn minus 1 non-linear term. Okay? So we do not have any non-linear term. Linear term, the simplest form. Okay? Yeah. So that's the linear. Okay. All right. Homogeneous. What's this homogeneous? Remember, there is no non-zero constant. Plus 1, plus 2, plus some non-zero constant. If there is no non-zero constant term, we call the homogeneous equation. That's the meaning of the homogeneous part. Yeah. Recurrence relation with constant coefficient. Yeah. So here the coefficient for each term, it's 1, that's constant. Because for some of the recurrence, you have non-constant coefficient. For example, here, let me give you an example. Fn equals n times fn minus 1 plus n squared times fn minus 2. That's the non-constant coefficient. N squared. Yeah. Much harder. Yeah. Here we have very simple constant. Yeah. 1, 1. Yeah. Yeah. Constant. Yeah. Very simple. Yeah. Yeah. All right, so that's the name of this equation type. Yeah. All right. The general case here, I want to show you. Actually, in your discrete math, you learn how to solve this type of equation. Yeah. In the discrete math. Yeah. But here, I want to do it again, and because I want to talk about some interesting problem-solving thinking here. Yeah. So we can learn some useful problem-solving thinking here. Yeah. So I want to repeat the whole solution process again. Yeah. Try to make a few points related to problem solving. Yeah. All right. Yeah. The general equation. So capital A, capital B, two constant numbers, but B cannot be 0. Yeah. If B equals 0, you get a first order recurrence relation. Too simple. Okay? So we assume B not equal to 0. So we get a second order linear equation. All right. Yeah, so the Fibonacci recurrence relation, just a special case. Yeah, all right. Yeah, yeah. But the procedure we follow here would be general. Yeah. So although we only work on the Fibonacci problem, but for the general problem, we can use this method. Yeah. All right. Solving Fibonacci recurrence relation. Yeah. So let's do some early discussion. Yeah. So I leave the solution next time. Yeah. So here, yeah. Take a special view. Yeah. Yeah. So yeah. So here, yeah. Actually, this story. So when we start with the story, yeah. Because we only have 3 minutes left, yeah, and yeah, let me delay, yeah, because otherwise I have to repeat it at the beginning of next class. Yeah. So let's just stop right here. Yeah. 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 All right. Yeah. So that's it. Yeah. Yeah. So on Wednesday, so we finish this part first. Oh, yeah. Let me tell you. I plan to do it Wednesday. Wednesday, we will start review sessions, review for midterm. Okay, yeah. But for first half, I will start module 4. The second half, I will explain quiz 1 questions. Now, in our review session, I will explain quiz 1, quiz 2, quiz 3, and homework assignment number 1 next Wednesday. Wednesday next week. Next week, right before our the test, because our online test, right? Online test, we do not need to use our class to do the test, right? So online test in the class, I will do the review covering the homework solution of the homework number 1. And after the class, I post the test. Because I give you up to the weekend, the weekend. So I post after the class. Yeah. So that's the plan, for the midterm. Yeah. All right. Yeah, that's it.